this morning here. It is my pleasure today, this morning, not to serve as general chair, but simply as a plenary session chair. And this morning we'll have the presentation by Christos Cassandras. Maybe you can come on stage already, Christos, who is Distinguished Professor of Engineering at Boston University, head of the Division of Systems Engineering, Professor of Electrical and Computer Engineering, and co-founder of Boston University's Center for Information and Systems Engineering. He specializes in the areas of discrete event and hybrid systems, cooperative control, stochastic optimization, and computer simulation. And he has been working also in terms of applications to computer and sensor networks, manufacturing systems, and transportation systems. Christos has published over 380 refereed papers in these areas and 6 books. In addition to his academic activities, he has worked extensively with industrial organizations and on various systems integration projects and the development of decision support software. And most recently, he collaborated with the MathWorks on the development of sim events, the discrete event and hybrid system simulator. A long list of editorial activities as well and awards he received. I will just focus on some of these, like the Harold Chestnut Prize, the Ifac Prize for Best Control Engineering Textbook, and he's also Ifac Fellow, and I should mention also him as editor for Automatica. More details in the manifesto that you probably have read through all the pages. And today, Christos will give a talk about autonomous mobility in smart cities, or automating mobility in smart cities. Recently, I was discussing with friends not in control, and some of them came to this idea that smart cities was a concept used by politicians to increase the control over the population, using new technologies, and in particular to automatically give fines to car drivers. Well, I was pretty much upset to hear so many familiar to us words with a negative point of view. So today I believe Christos will show us that control and automation will have positive impact on the complex issues in mobility for cities. Thank you, Christos.
Good morning, and thank you all for coming here today. And I want to thank the organizers in particular for inviting me and giving me the opportunity to share with you the work on automating mobility in smart cities. So I will start right away by trying to describe a little bit what we mean by smart cities, and Dimitri's comments are very much to the point. I don't want to get obsessed about detailed definitions or tedious semantics. I just want to put smart cities in the context of a systems and control setting that all of us here are comfortable and familiar with. Then I will move on to mobility, which I would like to look at as a resource contention game. And the reason I want to do that is in order to contrast selfish versus socially optimal solutions of such a game. The selfish optimality is what happens in a non-cooperative setting, such as the one that we have today when we drive. We drive selfishly, we do not cooperate with other drivers. However, if you contrast that to a potentially socially optimal solution, which comes from automation, then the gap between the two is what we refer to as the price of anarchy, and this is going to be an essential quantity that I'm going to spend some time on today. There are 2 takeaways from this talk. If you want, you can think of them as proposed research directions, because there's so many open questions that what I will be talking about today opens up. The first takeaway is how to use so-called big data in order to estimate this price of anarchy. More generally, though, the techniques, the mathematical techniques I will be talking about, really can be used in any setting in which you're trying to use data to infer from them something about the behavior of the players playing the game. So it has much wider applicability. Now, if I can convince you that in the context of transportation systems, the price of anarchy is large, then the second takeaway is that using connected, autonomous, or automated vehicle technology, I'll be using the acronym CAV, plus control methodologies, then we can reduce and, in principle, eliminate the price of anarchy. Okay, so here's my view of a smart city as a cyber-physical system, a term that I think most of us are familiar with. I view a smart city really as nothing but a closed-loop control system. And this closed-loop control system starts with data collection, and that is possible because of the proliferation of sensor networks, which in the last 15 years or so have become really ubiquitous. Then, after you collect the data, which are really raw, you process them and you turn them into useful information. This is where this notion of big data comes into the picture. And then the idea is to close the loop, make decisions, take control and optimization actions, actuate versus various devices, and close the loop. Of course, in order to do that successfully, you have to take into account considerations such as privacy, security, safety, energy management, because most of all of this system operates in a wireless, energy-challenged setting. All right, now why is this a cyber-physical system? Well, if you think about it, this part of the system has to do with networking. This is where you collect data and you just try to massage them and manage them. So, in that setting, it makes sense to use models that look more like this. They come from discrete event, the discrete event domain. Automata, Petri nets, the types of models that we use in networking. By the time that you get here, however, and you have to control physical devices, then of course it makes sense to go back to the more familiar type of models, differential equations, difference equations, because you got to model physical reality. Once you do that and you have various control actuation signals, you're back in the domain, the cyber domain, where you need to provide this information back to your devices, and then the devices, which are the actuators, turn this into reality. So, in my view, this is nothing but a gigantic, stochastic, hybrid systems. Now, not that by just calling it that, I've solved all the problems, but now we're in familiar territory. Okay, definitions of a smart city. There's many of them, and I just simply put some up there just to show you that there are several, and they come from different directions. For example, this one right here comes from an industrial organization. I've highlighted this one on the top right, which I've reproduced here, because this comes sort of from the technology point of view, which we're more familiar with. And it says that smart cities use information and communication technologies to be more intelligent and efficient in the use of resources. And that's the part that I like, because that's really where we come in and we can do something. All right. As I said, I don't want to dwell too much on definitions and semantics of smart cities. But no matter how you want to view smart cities, or as Dimitri alluded to, maybe not even believe that smart cities are a scientifically viable term, I'd like to show you a little video next, and I hope that we can all agree that what you see should be a component of what we view as a smart city. Okay, you get the idea. So, no traffic lights, everything flows, and what's interesting about this is that the first time that I showed this little movie, by the way, it's not real. However, by the end of this talk, I will show you in a controlled environment that this can be done. So, about a year and a half ago when I first showed this, the first thing that I said afterwards, I said, this is science fiction, but we're getting there maybe in a decade. Now I feel that I can safely say that except for the pedestrian, we can do this, okay? It's eminently doable. And I think that we will see this happening within 5 years, not 20 or 30. It is really happening. So the last thing I want to do before getting into the real meat of this presentation is a comment on the word smart. If you're like me, you're probably tired of hearing the adjective smart being attached to just about anything these days, grids, phones, cities, and so on. I just want to make a point, which for this audience is really preaching to the choir. And my point is that collecting data is not what smart is all about. It is absolutely a necessary condition to being smart, but it's not just being smart. And I'd like to illustrate that with one of my pet projects, smart parking. So if you look at the right there, the current state of the art of what I refer to as smart parking apps is that if there is an available parking spot there, this information will be given to you, and then you're pretty much left on your own to get there. Three problems with that. Number one, by the time you get there, you may not find that parking space available anymore. Number two, who's to tell that this is really a good parking spot for you? And number three, and more importantly, if the same information that's given to this little red car is also given to another 100 or so cars, then they all converge there for this one parking spot. One person takes it, and the rest drive around frustrated, creating more congestion. So that's anything but smart. What I think is smart is closing the loop, using feedback. So just using the information and then taking appropriate actions. In the case of smart parking, it means finding the best parking space for you, dynamically updating what is best for you, guiding you there, and reserving the spot for you. So that's all I have to say about, in my opinion, what smart is. Okay, traffic control in a smart city. In the top left, you see a snapshot from an infamous 100-kilometer-long traffic jam in China, which occurred about, I think, 6-7 years ago. It says here that it enters day 9. If I'm not mistaken, it actually lasted about 12 days or so. On the bottom right, what you see is something closer to home, my home, which is Boston. This is downtown Boston. This is a Google Earth map of this. There are two intersections right here. My office is here. And these are very, very tightly coupled. We call this the BU Bridge mess because this is the BU, Boston University Bridge. There's a lot of traffic coming this way, and then it has to be dispersed in various directions. But the main problem is that the coupling between these two intersections is so tight that what you observe here is deadlocks, real deadlocks, not mathematical deadlocks, real deadlocks. And I know this because I experience them just about every day. I'll return to this because this is going to be my kind of test bed environment for showing you how we can automate mobility. All right. So why on earth can't we improve traffic? I mean, we've been around for a while. We're all familiar from our day-to-day experiences with the problem of traffic control. We're smart people. Why is it that even if we know what can be achievable in traffic network, we seem to be unable to do it? I think there are two reasons for that. The first reason is that there simply aren't enough controls. If you think about it, there are tolls and speed fines, which are indirect mechanisms, incentive-related mechanisms, and there are traffic lights. And traffic lights are good, but they're very expensive. And in fact, only a very, very small fraction of intersections in the world has traffic lights for that reason. Therefore, there's no chance to unleash the power of feedback that we all know and love. The second reason is a simple game theoretic fact. If you don't know the other player's behavior in a non-cooperative environment, then that leads to poor decisions. And this goes back to what I said earlier about the contrast between selfish, user-based optimality versus system-based or social optimality. The gap between those two is what is referred to as the price of anarchy. It's an important quantity, and the first part of this talk is to try to see how we can actually estimate, measure the price of anarchy. But there's more here. Going beyond estimation of the price of anarchy, we should be able to reduce or eliminate it, and we have a chance to do that because of the advent of connected autonomous vehicles, which brings us to so-called Internet of Cars, which is, if you like, these types of labels, is a subset of the Internet of Things. Now, this gives us the opportunity to move from a selfish driver-optimal equilibrium of today to a social one because we have the ability to automate the decisions in the cars, basically take drivers, selfish drivers, out of the loop and find optimal decisions in some sense, which allow us to reach this social optimum. And then in the perhaps the most sensitive parts of a traffic environment, which are intersections, those are what the bottlenecks are, we can eliminate traffic lights and never stop, which is really the holy grail here. Never stop, always flow. And that's what I'd like to spend the rest of this talk telling you about. Now, obviously, I'm advocating self-driving cars, so I need to make a case for them. Here goes. First of all, humans are bad drivers. Okay? We are bad drivers. In fact, statistically, 94% of all accidents are due to human error. Computers do not get distracted. We humans do. Computers love data. They thrive on data. Humans cannot absorb data, and we know that we're now inundated by data from all sorts of aspects of your car and from the outside environment, but we cannot absorb and process them. Computers can maintain steady cruising speeds, which is very important in terms of energy efficiency, and we drivers seem to be unable to keep our foot on the pedal steady. If you look at signals that show you how speeds vary, even in a simple cruising situation on the highway, you find out that we're apparently unable to keep a constant speed. Computers react quickly. We humans typically do not. And when computers react, they tend to make fast and accurate driving adjustments. And finally, computers do not blink, they do not drink, they do not sleep. So I think it's very intuitive, and perhaps that's why the more general public is very accepting of this idea of self-driving cars these days. Of course, there's the opposite side. So there are objections to self-driving cars, and they start with legal issues. Who's at fault when there is a problem? How do you integrate these new technologies with the normal cars? That's a big problem. Security and privacy, but I would argue that this is not something unique to cars. It's something we all face in all aspects of modern technology. Accidents may be rare. In fact, I would claim that we can enhance safety with automation. However, when they occur, they're likely to be really bad, and you're probably all familiar with the infamous Tesla accident that occurred a couple of years ago that stirred some objections to this type of self-driving technology, car technology. And finally, there are technical challenges, obviously, and this is where we come in, and that's where I want to focus on. So, how do we quantify the benefits of this automation? This is the starting point. How can I convince you, perhaps not you, but others, that moving from the current state of affairs, which I call the before here, so this is my favorite intersection there. You see the tight coupling between those 2 points with traffic lights, so you see that queues form every once in a while, as opposed to the right-hand side, which is what happens when we eliminate traffic lights. There are no traffic lights here. Cars simply accelerate and decelerate judiciously to always move. And by the end of this talk, I'll tell you how we do that. So the question is, how do you quantify this? How do you come up with this price of anarchy? Well, the way to do it is with data. There's no other way. And we have been fortunate to have access to a humongous database of traffic data from the greater Boston area road network. So this is Boston, and this extends northwest and south, I would say, by about 40 miles. There are about 13,000 road segments. It's a humongous database. And what we have from that is speed data that we can convert to more useful forms of information. And I will show you in a few slides how analyzing the data from this particular road network for 1 year, 2012 in particular, we were able to estimate the price of anarchy. And what did we find? Okay, so no matter what road network you look at, it comes down to a graph, and there's a link in the graph. So I'll call it A. There is a flow associated with this link. I'll call it X sub A. And there's a cost function, which we'll call T. And now there are 2 different kinds of flows when you solve the problem in terms of the user-centric control. That's what we do now. So as a driver, you make some decisions, and this leads to an equilibrium of flows. And this equilibrium I will indicate with a superscript user, as opposed to a socially optimal equilibrium, which in principle is attainable, using socially optimal system-centric control, which I will denote with something in the superscript social. The reason I need this is to define the price of anarchy in this way. So the price of anarchy is a ratio, whose lower bound is 1, and the numerator here is the before. It's what happens today. There is an equilibrium today. I mean, we drive however we drive, but there are some flows and the corresponding costs associated with these flows, and that defines the numerator. And the denominator is the after. What would happen after automation? What would happen if I could optimize the network in some sense, typically minimizing congestion? Then I would be able to obtain this price of anarchy. And this is where the two takeaways from this talk really come into play. So number one, I'd like to find ways to measure or estimate the price of anarchy. And that I will do with what we call an inverse optimization approach, which I will explain. And if I can do that and show you that the price of anarchy is large, then that's motivation to move to the next step, to introduce connectivity, automation, to try to reduce or eliminate the price of anarchy. And I will try to show you an optimal control framework which will accomplish that. Okay, let's go with the estimation of the price of anarchy first. As things stand now, we have two major problems. Number one, we don't know the user cost functions. We all presumably make decisions as we drive, but we don't have an objective function. We don't solve an optimization problem when we take off from home every day. Yet, there must be something which leads to the equilibrium flows. Therefore, there must be an underlying cost function which corresponds to the solution that leads to that equilibrium. But we don't know what the cost functions are. We also don't know what the demand is for this network. That is captured by the origin-destination pairs, a huge matrix that defines the demand for any given pair of point A, point B, origin-destination. And that is a very difficult problem to solve. In the absence of this information, we can't solve the system optimality problem. I can't formulate a problem if I don't have objective functions and if I don't have an input, if you like, demand process. Which means I can't exploit automation. If I don't know how to solve the system optimal problem, what good will calves do me? I also can't assess the value of investing in this technology because I can't evaluate the price of anarchy. If I can do that, and I can show the price of anarchy is high, I will take my results, which are based on scientific evidence, which these days sometimes doesn't take you very far anyway, but let's say that it does, and I can take it to the city of Boston, I can take it to car manufacturers, I can take it to politicians and say, look, there's a case to be made here. And the bottom line is, despite these problems, we have lots and lots of data, and that's the key. So what I want to show you next is how we are using this data from this particular network in order to estimate the price of anarchy using this inverse optimization framework. So this, again, is our big road network, about 13,000 road segments, 50-plus gigabyte of data. And actually, the only data that we have at our disposal are speeds on a minute-by-minute basis for an entire year. Lots of data. The speed data are actually not terribly useful, so there's a process through which you have to convert this data into useful information, which are typically flows. These are better state variables for a setting. We can do that. I'll skip this step. And I will try to explain to you what the key idea is of this inverse optimization. So in the inverse optimization setting, there's a backward step in which you start with the data. The data reveal a selfish equilibrium. In a typical non-cooperative game, we call this the Nash equilibrium. In transportation systems, the term wardrop is used, but it's the same thing. Now, if there is such an equilibrium, there must be an optimization problem associated with it based on some cost functions which led to this equilibrium. Now, I call these virtual cost functions because I don't know what they are for you as a driver, not even for myself. But there must be something which, if we collect all the data, would reveal the best possible objective function that fits the solution of an optimization problem. If I can do that and estimate these cost functions, I can go forward. And I have a fairly straightforward optimization problem to solve, from which I can find the socially optimal traffic flows. So the backward step uses the data from the existing selfish equilibrium to estimate cost functions, and the forward step uses the output of this step in order to obtain optimal traffic flows in a socially optimal setting. And then, essentially, I have the information I need in this ratio that defines the price of anarchy to estimate it. So here's where I'm going to get a little technical, but not too much. The optimal traffic flow allocation problem in any network is a very well-known problem. In this particular formulation, I use a variational inequality problem setting. The X star represents the solution, the optimal traffic flows, if I knew what the cost functions are, which I don't. A little technical assumption here. If we assume that these cost functions are monotonic and continuously differentiable, this is a technical assumption, but it's very sensible, because obviously a cost function like this will be monotonic in the flow. The more flow there is, the higher congestion, higher energy, and so on. Given this assumption, there is a well-known theorem which says that there exists a unique equilibrium which corresponds to the solution of this variation inequality problem, which is called the wardrop equilibrium. This gives us simply a good, sound footing to go forward. Going forward involves doing these backward inverse optimization steps. So here what I'm trying to do is to use the data, so you can think of x sub k as a humongous vector of flow data that I have obtained from my traffic network. And what I'm trying to do is I'm trying to minimize the error in the fit between the data that I have and the cost functions that I would like to use. So ideally, I would like to make this 0. Of course, as you can see, this is a difficult problem because it involves functions. So we can't really solve it as it is. But if we are able to do that, then the end result will be cost functions that best fit this data. So the next slide translates the same problem into a complete optimization problem that looks a little ugly. And this will be done by using a reproducing kernel Hilbert space approach. This is how this optimization problem looks, and I don't want you to worry about anything except the objective function at the top, which combines what we call the data reconciliation component. So this is the component that says, I would like to make the best possible fit of the cost functions that correspond to my data. And the second term, which is what we call the generalization term, this is the term that if we have good cost functions data, will allow us to make good predictions in the future. And there's a trade-off between those two terms, and so what you see there indicated as gamma is just a weight that says which is more important to you, the reconciliation part or the generalization part. This is still a very difficult problem because it's still in function space. Ignore the other two decision variables. This is still a function. So what we do is we introduce the reproducing kernel, a family of functions that we think are good enough to find good cost function estimates. So we chose this particular family of functions. See, it's some kind of a polynomial. And essentially what I have done is I have converted the previous optimization problem into one that now involves parameters. Instead of functions, I've got parameters. Still, an ugly-looking big problem, but we can solve it. And when we solve it, we come up with a link cost function estimates that look like this. So you see that the solution of this problem appears in this family of cost functions. So I'm almost there. If you recall, I had two challenges. One, I didn't know what these cost functions were that corresponded to an existing selfish equilibrium. Now I have an estimate of what these cost functions are, virtual cost functions. And the second part is the demand. What is this OD matrix that I need to use in order to build my forward optimization problem? Well, that's a separate and pretty challenging problem, which I'm not going to talk about here. I can tell you that we can also solve it using a generalized least squares type of method. And in fact, this afternoon, in this session right here, I'll talk a little bit about this problem. I also want to point out that this is a humongous problem, because when I talk about origin-destination pairs, I mean literally linking potentially every point in this big network as a potential origin and potential destination, including situations like you see here. This origin and this destination, and this origin and this destination share several links. So even if I know the flows on links, I don't know which OD pair they correspond to. So I have to kind of extract this information, which is hard. And typically, there are hundreds, actually more like thousands, of these OD pairs that we have to extract. But let's say that we did this, and now we come to the second step, which is the forward step. Now, the forward step is simply a nonlinear programming problem, fairly straightforward, which includes the estimated cost functions, so these are now well-defined, and the feasible flows that come from this OD demand matrix. So that's why I needed these two steps, to be able to formulate this problem. Once I solve this problem, I've got my optimal social flows. So I have the equilibrium flows from the real data, that's the numerator of the price of anarchy, and now the solution of this problem will give me the denominator. The results I'm going to show you for the Boston area traffic in this particular presentation are limited to this subnetwork from the big one that I showed you. We have since gradually scaled up. It's not easy. It takes some effort, but we're getting there. And on the right-hand side, you see typical forms of the cost functions that we have estimated. Not surprisingly, as the flow increases, the cost increases in this asymptotic manner, as you might expect. And these are the results that I want you to take a good look at. These are really interesting. These are results which show you, for different links, I've just selected a sample of them, the red lines, for example here in link 0, correspond to what's happening today. So this is the average flow in this particular link. You see underlying the blue data. So the red line is simply the average over a certain period of time. And the green line is the optimal, socially optimal flow. So what do you see? And I've highlighted a few ones. You see some links where the socially optimal flow should be higher, some links where the socially optimal flow should be lower than what's happening today, which means that you have an imbalance. But just eyeballing all of this, except for some cases where it looks like the social and the selfish optimal flow are already almost the same, this is telling you that there's opportunity for improvement here. If we could rebalance the flows by, for example, diverting some people who are here to here, then we should be able to do better. And the next slide is going to show you the actual plot of a price of anarchy curve, which looks like this. I remind you that this is the definition of the price of anarchy. This is what you see on the y-axis here. So the minimum that you can achieve is 1. And this is for the month of April of 2012 over all the days in April in some afternoon period. Now, this is what's really intriguing. There are cases where the price of anarchy is actually greater than 2. That tells us that there's an opportunity to reduce congestion, energy, emissions to the environment by more than 100%. On the average, I believe this turns out to be about 1.5 or something. So this is it. You take this evidence and you say to the city of Boston, there's an opportunity here. To the car manufacturers, it makes sense to go with this connected autonomous vehicle technology. To the politicians, it makes sense to invest in an infrastructure, which actually is not very much for these types of technologies, and move towards automation, because I can eliminate this price of anarchy by using automation. If I can direct the cars automatically to go the way I want them to go because that is socially optimum, I can, in principle, get the price of anarchy down to 1, its minimum point. So, goal 1 is essentially accomplished. I have found out how to estimate the price of anarchy from real data. And I have actually observed that it's high, which means that we have an opportunity to move from the selfish to the social optimum. How do we do it? That's the next step. And the idea is to eliminate the ugly world of anarchy and move to a world of, let's hold our hands together, kumbaya, praise the Lord, and everything is nice. So that is where I'm going to go next. Now, there are several ways in which we can exploit automation to accomplish this. The first step is routing, and my claim is that that's relatively easy because already, in a sense, we have the ability to do that. When you use your Google Maps app or your Waze app, wherever you are in the world, depending, actually you get recommendations for where to go. Now, I'm not saying these recommendations correspond to a socially optimal solution, but let's say they were. Let's say we start working with Google, we supply them with all these methodologies to find the socially optimal solution, and then this translates into an app. And then let's say that people more or less follow these recommendations. So we're kind of doing that in a sense. Moreover, this is where incentive-based mechanisms, pricing schemes can come into play. If I know where the social optimal routes are, I can perhaps entice all of us to follow them. And ideally, ultimately, if the cars are really completely automated, then the minute you get into your car and you say, that's where I want to go, then the car takes over, finds the optimal route, socially optimal route, and that's it. What's more challenging is a situation, again, like this one here. The real bottlenecks of an urban traffic network, the merging points and the intersections. So what can I do to automate the way in which vehicles move through intersections like the ones you see here? And this brings me to the last part of my talk, which is an optimal control framework for CAVs so that we can accomplish this. No traffic lights, never stop. I want to underline the word decentralized because I think you'll agree with me that if this is to be really realistic, it's got to be done at the level of a car. You don't want to have a central controller sitting at every intersection telling every car what to do. So decentralizing the optimal control solutions of the problems that I will describe next is very important. First of all, I want to say that this is not really a new problem. It comes under the header of vehicle coordination problems whose solutions typically fall roughly under centralized and decentralized approaches. I've listed here several contributions to this vehicle coordination technology. You can see from the dates that most of them are recent, but look at this. I think you'll recognize names from our community who have made contributions as far back as the 60s in terms of this problem. Also, this gives me an opportunity to acknowledge related research that's taking place by people in our community. Perhaps some of them are in the audience already. It's very interdisciplinary research, so it's not easy to create a team of control people, systems engineering people, communications people, optimization people to all work together. And I've listed here a sample around the world of groups that I am familiar with because I have interacted with them. And the last one I've highlighted because this is a group that I'm currently collaborating with at the University of Michigan. So, how do we do it at an intersection? This is an intersection, and the first two elements are this circle, which indicates what we call a control zone. So the minute that vehicles enter this control zone, they enter the region within which we're going to apply optimal control and hopefully trying to make them to never stop, and there are no traffic lights. And there is a coordinator here, but it's not a controller. So the role of the coordinator is simply to collect data, maybe pass on some information between the infrastructure and the vehicles, or facilitate vehicle-to-vehicle information passing, but no control. Then there are cars that arrive, and they enter, and as soon as they enter the control zone, they get an ID. So this is number 1, and number 2, number 3, and so on and so forth. And ultimately, you can have two intersections, like the ones that I've been referring to, which are very close to each other so that the control zones actually overlap. Each one has its own coordinator. And notice that there's also another region called the merging region here, which is actually where the contention takes place. So you really don't want to have too many cars in here that may collide. And I have to guarantee that they don't collide, of course. So I need to build a model. The first steps of the model are the CAV dynamics. These are fairly straightforward. Our control is going to be the acceleration here. There are two critical times: the time when you enter the control zone if you're vehicle I, and the time when you exit the merging zone here. There's also some constraints, which are the physical constraints imposed by limits in the speed and acceleration. So that's pretty standard. As I said, there are these two critical times: when you enter the control zone, when you leave the merging zone. And there's one more, which is when you enter the merging zone. So what I'll try to do is essentially build an optimal control framework for what to do between this point and this point. And there is a list of vehicles which is associated with the control zone. For example, here I've got 6 in there right now, so n of t would be 6. And I'm imposing an order which says the ith vehicle must leave after or the same time as the ith minus 1. So 5 must leave after 4, for example. But that does not mean that I'm imposing a very constraining first in, first out limitation. I'm not saying that the first guy who enters here, the number 5 guy who follows the number 4 guy must always be leaving or entering the merging zone after 4. This order could be changed at certain events, typically when vehicles arrive. So it's not a constraining type of inequality. Next, I need to say something about the physical topology that links to vehicles like I and I minus 1. And there are really 4 cases. The first is that when vehicle I arrives and enters the control zone, vehicle I minus 1 may be in the set of vehicles which are on the same road as I, but different lanes. Or they could be on the same road and the same lane. For example, 4 and 5 are in the same lane, moving in the same direction. Or they could be in different roads, which actually could create a collision. For example, this guy and this guy could eventually collide here. And finally, I could have a situation where they're on the same road, but in opposite directions, but with no possibility of collision. For example, 3 and 4. And that's it. And that is easily determined. It's just topological information. A couple of assumptions. We will assume here no turns and no lane changes. This can be relaxed at the cost of some increasing complexity. And I will also assume that the minute you arrive at this merging zone, you go through it with a fixed speed. And that makes the connection between the final time and the merging time easy to determine. And this is for simplicity and can also be relaxed. And finally, of course, the 2 safety constraints. The first one is the rear end safety constraint. You don't want to allow 2 cars to get too close to each other, and you want to do that automatically. I'll use the subscript K to always denote the guy who is in front, physically in front of I, not necessarily I minus 1. And so the safety constraint is this simple inequality where delta here is the safety distance. And then we have the lateral collision avoidance constraint. I don't want 2 cars like that to be in this blue area at the same time. So what this says is simply within a certain time interval that corresponds to when this guy is in the blue area, this guy is in the blue area, I can't have them there at the same time. So now I can formulate this energy minimization problem. And the important thing is that I choose to minimize an energy metric of each car, which is the square of the acceleration, which I'm not an expert in how to model energy consumption in vehicles, but I understand there are standard models for which this square quadratic type of expression is good enough. The rest is just the constraints that I've already been talking about. Notice the bottom here that the arrival time and the arriving speed of the vehicle in the control zone are given, but this formulation seems to also require knowledge of the final time in the optimal control problem. Where does that come from? Who decides what that final time is? So that's missing. I'll tell you how we determine that after simply giving you this definition, which simply says that this symbol here captures the feasible control set, so that I can formulate a throughput maximization problem. So in this problem, if you look at this term, this is the term that captures the distance between the time the two successive cars arrive at the merging zone, or, if you notice the cancellation of a lot of terms, ultimately it's really the time between the first and the last, or current, vehicle in the control zone. And that is sort of like a throughput maximization term, subject to all the constraints that I have already. So here comes the first real analytical result. The solution of this problem has a recursive structure. In other words, vehicle I can determine its optimal, in the throughput sense, time at which it should arrive at the merging zone, the final time of the optimal control problem, because you see on the right-hand side, everything is known. It's either things like information from I-1, which comes from the previous vehicle, or K, which is the physically, if any, vehicle present right in front of I, which is already there, or the only other unknown quantity is this TIC, but this turns out to be just a constant, which has to do with the constraints on speed and acceleration. So I got to have something like that. But the point is that the entire solution of the throughput maximization problem can be determined in this simple recursive manner. This is a summary of what I just said. The throughput maximization problem delivers optimal solutions for the target final times, which I can then plug into the final time of this optimal control problem, which is the energy minimization problem. And this now permits me to decentralize these problems. So in this decentralized setting, I need an information structure for each vehicle. And the information structure is this. This is the information that every vehicle entering the control zone here needs to have at its disposal. These three quantities are pretty obvious. It's my own position, my own velocity, and my own distance from the guy in front of me, if any, which I assume to be measurable. The remaining terms are, W is just a unique ID. So this is where the coordinator comes into play. When somebody arrives, the coordinator says, okay, this is your unique ID, so we know who you are. Q sub I is the set, which is one of those four sets that I defined earlier, that gives you your relative topology with the guy who has an index I-1. So if it's 5, it gives you, it puts you into the set of 4, which is in the same lane, same direction. And finally, this is the last piece of information that the Ifac needs to know. It needs to know its target final time in this optimal control problem, and this comes from the solution of the throughput maximization problem. So, 2 final comments. The information set is always available to cav I upon arrival with the help of the coordinator, and, of course, I need communication. Can't escape that. Communication may be between the coordinator and the vehicles, or perhaps between the vehicles directly. That remains to be decided. There's a lot of work going on protocols, which eventually will become the standard of how cars talk to each other. One example is the so-called DSRC, which stands for Direct Short-Range Communication. You can think of this as something between Bluetooth and Wi-Fi. So Bluetooth is too short, Wi-Fi is too big. DSRC is something in between, which might be okay for cars which are within a range of a couple of 100 meters from each other. But communication is important. So finally, we have this decentralized problem that every individual cav needs to solve. It solves its own energy minimization problem, but the final time here has already been determined by a throughput maximization problem. Absent from this formulation, though, are the 2 safety constraints. The first is implicitly handled by this particular quantity. That's just the way it turns out. The second is the rear-end safety constraint. It's not there. And it's only guaranteed for the final time, again, because of the way that this was determined. So these question marks basically say, what's going on here? You can't guarantee one of the most important constraints of your optimal control problem. Where are we going? In fact, it's pretty bad in terms of guarantees this constraint, and this is an example that shows you that vehicles 2 and 3, which are adjacent to each other, this is their position profiles over time. This number 10 here is the safe distance between them, and you can clearly see that the optimal control selected for vehicle 3, for whatever reason, put the vehicle way too close to vehicle 2 inside the control zone. So this is something that I could not have even really anticipated before entering the control zone. So we have a problem. Let's skip that for a second, pretend that this problem isn't there, and solve the optimal control problem. First, without any constraints. And you see that the optimal control solution is actually fairly simple. It's a linear function of time. The optimal speed and position follow suit. And the coefficients, A, B, C, D, can all be determined by a simple set of linear equations. So the optimal control problem is not terribly hard in principle to solve. If constraints are active, there are about 6 different cases that can arise. If I remember correctly, the solution is still the same, still tractable. It just takes a little bit more work, and there's a paper that provides the solution. And now let me return to this key issue. I still cannot guarantee the rear end safety constraint for every point throughout the control zone. So that's a problem. We have a theorem that says that there exists a non-empty feasible region of initial conditions for each vehicle such that we can guarantee that this safety constraint can hold. Let me just simply copy the theorem and show you its visual representation. It says that if you could identify the initial time and the initial speed of a vehicle, then there is a large, in this case, feasible region, so that if that vehicle arrived at this time and at this speed, no problem. We can guarantee safety throughout. But if it arrives in here, we cannot. In fact, it makes sense. If you arrive too early and with too high a speed, I can't guarantee that I can keep you within a safe distance of the guy in front of you. So this basically says that it's doable, but I'd have to make sure that the initial conditions are appropriate. How do we handle that? Well, we handle that one way by creating an extra ring around the control zone, which we call the feasibility enforcement zone. And in that zone, we don't care about optimality, we just care about feasibility. We're just trying to drive the vehicle into a feasible region. And if you do some worst-case analysis, you can come up with something which gives you a worst-case length of that feasibility region. Another approach is to say, well, you know, if that happens, I can detect it upon entering the control zone, and I'll simply give up optimality and just simply worry about safety. And that's possible. So there are ways to get around that, but it's a problem, and it's not surprising to anybody who does optimal control with constraints. It's hard to guarantee feasibility of all your constraints throughout the duration of the optimal control problem solution. So back to my favorite intersection. Now you can perhaps appreciate a little bit more what happens on the left with traffic lights, what happens on the right without traffic lights. If you look carefully, you'll see that some cars, for example, this one came pretty fast and then slows down to just make sure that everybody goes through without ever stopping. And this is doable. We've done it with a lot of simulations, and we've done it in the lab environment as well, and I'll have a little bit more to say about that in a minute. But now I'm also in a position to tell you what the bottom line benefits are, and they are very encouraging. This is really a win, win, win situation. You can reduce your energy, fuel consumption, for the example that I just showed you, by roughly 46%. You can improve your throughput, or reduce equivalently your average travel time, by roughly 30%. And in fact, in almost all the cases that we have looked, 40% seems to be the magic number. It seems that between fuel consumption and throughput, you can always have a benefit of roughly 40%, which is pretty impressive. The third win is that if I can manage to do what I'm describing and never stop, then I avoid this stop-and-go situation, which is where all the dirty gas emissions manifest themselves. So I have the triple benefit of also benefiting the environment. Testing. Well, we always need to test beyond simulation environments. And so on the right, I have a picture of M-City, which is an area where this is a physical area where you can do testing with real cars. And I'll be working in a new project that I have in this area. But On the top left here, I'm showing you our Boston University robotics lab, where we have kind of a halfway point where we can at least do some things in the lab. So in this lab, what we do, this is the floor of the lab, and we project from the ceiling different landscapes. So in my case, I wanted a landscape that had a few intersections and urban blocks. And these are traffic lights. So we project traffic lights. In this case, we were doing an experiment where we're trying to optimize traffic lights. So you can see that the vehicles stop and go when the light is red and so on. And these are little, tiny mobile robots, which are my calves. And I can have them talk to each other or to a coordinator, and I can run various experiments. So you've got your simulation setting. You've got your real-world setting. But as far as I know, this is the only one in the US. So it's pretty expensive. And I'm told that when we eventually will test some of our smart cars here, it will cost us a few tens of thousands of dollars for like an hour of testing. So this is the halfway point, which I think is interesting and makes it actually exciting, and students love it. Now, as far as the optimal control framework is concerned, the story is not closed. There are several issues. The first one has to do with, is it feasible to run such an optimal control problem solution in real time? Our indication so far is that yes, you can. And in fact, if you are prepared to adopt event-driven techniques, which you can, then you can make things even more scalable and manageable. Incorporating turns and extending to multiple intersections is fairly straightforward, except for the fact that you will have to pay the computational price. You can seek alternative optimization formulations to combine these two key objectives. And this is key. How do we incorporate pedestrians? How do we incorporate non-CAV traffic? This is the questions that I'm always asked when I give a talk like that. And I have some partial answers, which I'm not going to give you here, but I'll be happy to talk to you about it. There are ways to get around that. So, in conclusion, as I said, there are two takeaways from this talk. And I really hope that you can look at them as proposed research directions, because each one of them really opens up some very interesting perspectives. The first one is the inverse optimization idea, which extends beyond estimating the price of anarchy in traffic networks. It really has to do with embracing the data that you're given in any non-cooperative game situation and using those data to infer something about the behavior of the players. And these players, in this case, are drivers, but they could be humans playing other resource contention games in other situations, or more generally, agents that play these games in a multi-agent system framework. The second takeaway is really that we have a tremendous opportunity to use connectivity and autonomy, and I want to emphasize here that both of these are equally important. In fact, connectivity may be more important than autonomy in some cases, but if you use this technology and combine it with fairly standard control optimization systems, methods that we all know and love, then we have a chance to really build I think, a lot of new research thrusts that keep us busy for years to come. Looking into the future, in the context of automating mobility, I think there are some really interesting questions. The first one is, what fraction of these calves do you need before you can realize the benefits of automation? Is it 2%, 5%, 80%? If it's 80%, that's not a good story. We'll have to wait until people can afford to buy connected automated vehicles, or through policy making or whatever, we eliminate existing vehicles. So this is a really interesting question. People have been trying to come up with estimates. I'm not sure that we know the answer to that one yet. My hope is that it would be no more than 10%, but I think that's a little optimistic. How do we integrate cabs with pedestrians, bicycles, and so on? I alluded to this question before. We have answers to these questions, but I will not, comment on that right now. And this may be the ultimate solution to our traffic problem: shared mobility on demand. Because if we start making smart cars, which are affordable, and we all start buying them, the end result is that we'll have more cars on the road, because everybody will be buying them. It'll be so nice and comfortable to get into your car in the morning, push a button to take you to wherever you want to go, and then snooze or read the paper or do your email. And so that may be ultimately bad. So maybe the solution is to just share a smaller number of cars that always move. In fact, if you think about it, your car is utilized about 4% of the time. It's one of the major investments we all make in a lifetime, buying a car. And yet, this great investment is utilized 4% of the time. That's terrible. It's a terrible investment. That, if you're a rational person, says maybe we should all be sharing nice cars, and then we have fewer cars on the road, and in fact, that will solve the parking problem as well, because cars will never have to park. They'll be just moving around, serving us. And lastly, none of this is ever possible without the help of many past, former students. Often it is those students and colleagues that deserve most of the credit, and we, the speakers, are just the mouthpieces of a lot of hard work that goes into this research. And of course, several sponsors from federal agencies, City of Boston in my case, and several industrial partners. And with that, merci beaucoup.